Hey everyone, this is Nick from Engineering Today, and on this special episode of Page by Page, we're going to be going over Chapter 2 of Crafting a Compiler with C. It's going to be a lot of fun today. It's a Wednesday, like I said. It's nice and sunny outside. It's the first time that it's actually not been raining here in, probably like 2 weeks now. So that's nice. But hey, we talked about computer architecture yesterday. We're going to talk about compilers today. Everyone's going to have a great time. I'm having a great time, I know for sure. Okay. Let me make sure everything's up and running. I think it is. Looks like it. Great. Okay, so last time when we were talking about crafting a compiler, we really just talked about what is the job of a compiler, and we saw that that was to take some arbitrary high-level language and turn it into some lower-level language, typically something like assembly. We saw there can be many different flavors of compilers for many different languages. Some of them focus on just-in-time compilation for things like Java. Others are more classical compilers like the GCC compiler. And we saw that GCC actually isn't just a compiler, it's an entire framework with numerous front ends for Java, C, C++, etc., etc. I think even Fortran is in there. So today we're going to dig a little bit deeper into this idea of how do we construct a compiler by going over a simple example compiler. Okay. So let's see. Let's get the highlighting tool out. Great. And let's begin. So in this chapter, we provide an overview of the compilation process by considering a simple translation task for a very small language. So we're not going to jump into doing something hyper-specific just yet. Or we're not going to jump into, say, trying to rebuild GCC's compiler portion. We're going to keep it simple. We're going to use a very reduced language. It doesn't have a ton of functionality, but it works. So to simplify both the presentation and implementation, we're going to break this up into phases. So we're going to give us some layers of abstractions. We're going to tackle each phase of compilation piece by piece. So each phase is going to be responsible for a particular aspect of the compilation process. So the first thing we're going to do is we're going to analyze the syntax of our input program. We're going to make sure that what we're reading in is valid based upon our language, so syntactically valid. We want to make sure that we have keywords that are spelled correctly. We want to make sure we don't have illegal characters, so on and so on. So we do this with the goal of generating an abstract representation of the program's essential information for translation. So we want to cut out anything non-essential. So if it's a comment, we don't care about it. If there's extra white space or new line characters all over the place, we want to strip those out. We just want these small bits that carry all the information. And generally we call those tokens. So sometimes this phase is called tokenizing. So the subsequent phases analyze and transform the tree, eventually generating a translation of the input program to the target language. So we're trying to get to this target language. So this is going to be something like some ARM assembly language or x86. That's the goal, but we're going to have a very reduced instruction set that we're probably going to target in this book. Let's see. Okay. So we're going to call this language AC. The AC language and its compilation are sufficiently simple So yeah, we're just going to use this language that we're going to call AC. That's going to be our target for this. And so they actually have the complete form of the code presented here in the Crafting a Compiler supplement. I'm sure we can find this online sometime, but for the most part, we want to learn the compiler theory first. We don't want to just copy code and use it. We want to know a little bit more about how it works on the inside. So this is going to start right here at 2.1, where we have our informal definition of a language. So we're going to do something pretty simple. So this is for our adding calculator language. So when compared with most programming languages, it's a relatively simple one, but it serves nicely as a study. And typically that's what we want to do. If we want to test out some ideas, we generally want to keep it simple first and then build upon strong ideas. So what are the things we're going to have in here? We're going to have types, of course. So most programming languages offer a significant number of predefined data types with the ability to extend existing types or specify new data types. So in AC, there are only two data types, integer and float. So we're not going to do anything special. We're not going to do any type defs. We're not going to do double precision. We're not going to do unsigned numbers, just integers and floats. So integers, as a reminder, is just a sequence of decimal numbers. And then a float gives us some fractional numbers. And so a float for us, a typical float, allows for 5 fractional digits after the decimal point. So obviously we're not doing IEEE 754 floating point standard. So keywords. Most programming languages have a number of reserved keywords. So things like if and while, we'll call those keywords. And so we want to make sure that we can distinguish these from other variables. Say, so f and I are also going to be keywords, it looks like, for float and integer. But we want to distinguish all of these from a variable name. So if we have a variable called, A or B or C, that would be valid, but we can't have a variable called F or I. And then, of course, variables. So some programming languages insist that a variable be declared by specifying the variable's type prior to using the variable's name. So the AC language offers only 23 possible variable names, drawn from the lowercase Roman alphabet and excluding the 3 reserved keywords, F, I, and P. So we're using just normal characters, so A, B, C, D, E, we skip F, G, H, we skipped I, L, M, N, O, we skip P, and then Q to Z. And then, of course, so we define early on that we have to declare these prior to using them. So most programming languages have rules that dictate circumstances under which a given type can be converted to another type. So this is we're talking about casting here. If we're going to cast, say, an int to a float or a float to an int, that's what we're talking about. So in some cases, such type conversion is handled automatically by the compiler, while other cases require explicit syntax such as casts, to allow type conversion. So in our small calculator language, the conversion from integer type to float type is accomplished automatically. Conversion in the other direction is not allowed under any circumstance. So we can turn an integer into a float, but we can't turn a float back into an integer. Good things to know before we start building. So for the target translation, we use a widely available program, DC. So we want to translate our language AC into this DC language for desk calculator to, I think it was adding calculator. Okay. So we're going from AC to DC. Somebody probably had some fun with that naming. So, which is a stack-based calculator that uses reverse Polish notation. I'm not sure what this is yet, but I guess we'll figure out a little bit later on. So when an AC program is translated into a DC program, the resulting instructions must be acceptable to the DC program and must faithfully represent the operations specified in an AC program. So we need to make sure that after we do this translation, we're not doing something wildly different than we wanted in that AC program. Maybe our path to get to that endpoint is a little bit different, but we're still reaching these same end results. So stack-based languages commonly serve as targets of translation because they lend themselves to compact representation. So things like Java into JVM, ActionScript into AVM2 for Flash media, and then printable documents such as PostScript. So this is used by printers. Thus, compilation of AC to DC can be viewed as a study of much larger systems. So we're kind of abstracting away a lot of the difficulties of doing a fully fledged language like Java or something like PostScript, and we're saying, okay, well, we'll get the key ideas from this small language. So figure 2.1, here's a context-free grammar for AC. Okay, and we'll talk about this a little bit later. So formal definition of AC. So now that we've had this kind of high-level view of what do we want AC to do and what is AC made out of, now we need to be a little more formal so that we can actually start looking at how do we design a compiler for this. So before translating AC to DC, we must first understand the syntax and semantics. So we need both. So we therefore follow the examples of most programming languages, and we use a context-free grammar, or CFG, to specify our language's syntax and regular expressions to specify the basic symbols of the language. Okay, so let's talk about the syntax first. So while context-free grammars are discussed in detail in Chapter 4, we presently view a CFG simply as a set of productions or rewriting rules. So a CFG for the AC language is given in 2.1. To improve the readability, multiple productions for the same symbol can be specified using an arrow for the first production and bar symbol to separate the rest of the productions. So for example, statement serves the same role in each of the following productions. So I think they're saying here that some statement can be translated into, can be built from ID, assign, value with some expression, or a statement can also be print ID. So that's what we mean. Some statement here can be formed from two different things, and we separate it by this or, this bar, this pipe. So it can either be some ID, assignment, some value with some expression, or something like a print statement. So these productions indicate that a statement can be replaced by one of the two strings of symbols. So we can kind of start breaking down this language into more compact parts. So if we have some long line of code, we see that we can break this down to, okay, well, this is a statement. And then the same thing with the print ID. We know this is another statement. So in the first rule, statement is rewritten by symbols that represent assignment to an identifier. In the second rule, statement is rewritten by symbols that print an identifier value. So we can represent this statement one of two ways. So productions reference two kinds of symbols, and these are terminals and non-terminals. So a terminal is a grammar symbol that cannot be rewritten. So here we can rewrite statement as either this expression ID, assign, value, expression, or as this print statement. However, if there was nothing here, if say, none of this existed, then that would be a terminal. So up there we actually have an example of a non-terminal. Okay. On the other hand, figure 2.1 does contain productions for the non-terminal symbols above, val, and expression. So if we go back to this context-free grammar, we see that val can still be replaced by something else, this ID, and expression can be replaced by something else, either this or this or this. So we have mixtures of terminals and non-terminals in here. So let's see. If we look at print, so print must be a terminal because print can't be rewritten as anything. However, if we look at something like ID in this list, or no, maybe not ID. Let's go with value. So value in this list, value has a spot up here and can be rewritten as ID. So that's a non-terminal. Okay. So consider a context-free grammar for some programming language of interest. The context-free grammar serves as a formal and relatively compact definition of all syntactically correct programs for that programming language. So it's really just a compact way of defining the entire language as what expressions are valid and what are not. So if it's not in the list, it's not valid. So to generate such a program, we begin with the special non-terminal that we call a start symbol, which is usually the symbol on the left-hand side of the grammar's first rule. For example, the start symbol here is this prog, which will mean something like program. So some program is made up of declarations and statements. Some declaration, it can be made up of more declaration or more declarations. A single declaration can be made up of floats and ints, followed by IDs. But it all starts at this prog that we can just consider to be something like program. Okay. So from the start symbol, we proceed by replacing it with the right-hand side of some production for that symbol. So we continue by choosing some non-terminal symbol in our derived string. So we need to constantly pick non-terminals unless we want to end the program. So we need to continue going down this list, constantly doing these kinds of replacements until we're finished. Okay. As a special case, the symbol lambda denotes the empty or null string, which indicates there are no symbols on the production's RHS, which is just the right-hand side. The special symbol, this $, is the end of an input stream or the file. So we kind of have, so we really just expand out this statement right here. This program, we'll highlight it in, say, red because it's more important. We highlight this statement because this statement, in effect, captures the whole program. Just through a series of expansions. Okay. So what we do is we continue applying productions, rewriting non-terminals until none remain. So any string of non-terminals that cannot be produced in this manner is considered syntactically, or that can be, is considered syntactically valid. So a string has a syntax error, it would not lead to a legal program. So if we have some string that we can't create using this set of rules, it's syntactically invalid. So to show how the grammar in 2.1 defines legal AC programs, the derivation of one such program has been given in figure 2.2, beginning at the start symbol, program. Each line represents one step in the derivation. So let's see. So we start out with something simple, just program, which can be written as declarations and statements, which can be written as a single declaration with more declarations and statements. This declaration we can use to define a float. This declaration again can be made into more declarations and statements. This declaration can be made into another into this declaration of an integer this time, with still more declarations. So then if we go back up here, we see that a declaration can also just end. It can be a lambda, so a null. So then the declaration goes away, and we're just left with statements. So we're going to focus on statements now. So a statement can be broken up into one statement with multiple statements following it. We can change this statement, this first one, into an assignment of a value and an expression with still more statements afterward. And so we can change, let's see what we're focusing on now. It's going to be this value. So this value is going to be an integer. And then we still have an expression here. The expression, let's see, can we get rid of it using that symbol table? So expression can also be lambda, so we can just get rid of it if need be. Left with more statements. So we get rid of the expression, we're left with statements. We create another statement, so we can break statements up into a single statement with multiple following statements. We turn this statement into an integer assignment to a value. And we assign that value to some ID. So then we have this expression afterwards still. So then this expression can be transformed into some expressions. So in this case, we're using an addition. So expression can either be plus or minus. So in this case, we're using plus. This val or value gets transformed into a floating point number. We're still left with expressions, but we can get rid of it because it can go to lambda. We're still left with statements. We break this statement up again into a single statement and multiple statements. We turn this single statement into a print. We finally are at our last line where we have multiple statements, which can just go away, because if we look back to this context-free grammar, a statement or statements can just be lambda. So it can be nothing. So if we think lambda, we can think of, okay, it can either be something or it can be nothing. So in the case of statements, it can either be broken into a single statement with multiple statements following, or just lambda, or nothing. And then, of course, we have this $sign representing the end of our program, which goes all the way back to the beginning. Okay. So now we can start defining some other things. So using what's typically called, or not what's typically called, what is called regular expressions. We can define specific keywords or specific statements here that have meaning for us in our program that we can use as tokens. So that's what so this is a formal definition of the tokens, and we can put all our program through a tokenizer, and it will split it up and it will classify our program into these bins. So for float, for integer, if we ever see an F in our program, that's just by itself, it's a single character. we'll just take it and we'll rewrite it as just a float or a float decimal. Same thing with integer. Prints, p will just be replaced by a p. So for some ID, it can either be any letter from A through E, or any letter from G through H, or any letter J through O, or any letter Q through Z. Assignments, plus and minus, have special meaning in our language. So we give them keywords, or we give them their own regular expression, so we can pick them out. We say that some integer number can be 0 through 9 plus, which means that it can either be, it has to be one or more of these characters. So it can be something like 0, or it can be something like 0, 1, 2, 3, 4. However, we can't have it be no digits. It has to be at least 1, and that's what this plus says. Now for a floating point number, it says the same thing, but with a decimal point this time. So this says I can have any number. I can have 0.0. I can have 123.456 going on forever. It just says I need to have one number on both sides of this decimal point. And then for blanks, whenever I see a blank, it has to be one or more for me to classify it as a blank. Okay. Very good. So that's going to be our definition of token. So what do we have so far? So we have a context-free grammar that defines what's syntactically correct in our language. So what is the ordering of these expressions? If we can translate some program into this context-free grammar, we know that it's at least syntactically correct. What do we also have now? We have a way of going from some program of characters now and turning them into these identifiers, or these tokens. So let's talk about token specification. So far, a context-free grammar formally defines sequences of terminal symbols that comprise a language. The actual input characters that could correspond to each terminal symbol must also be specified. So this AC grammar that we saw in 2.1 uses the assign symbol as a terminal, but that symbol will appear in the input stream as a character equals. So we'll just rewrite this equals whenever we see it as assign. So we also see that F, I, and P in our language are reserved for special use, so we have to make sure that we're picking those out individually. So the formal specification of a language's tokens is typically associated by, or it's accomplished by associating with a regular expression. Silver Pikachu 1, engineering today, you should upload all your VODs to YouTube. And then he saw that I did. Hey man, of course. I'll always upload all my VODs to YouTube, man. And listen, we've got some short form content coming real soon. And like I always say, you never have to donate to the stream. You never need to worry about that. I'll never put anything behind paywalls. If you want to buy me a cup of coffee, that's as high of a stream goal as I'll ever set. So let's continue on. So the specification in figure 2.3, so where's 2.3? So 2.3 is this definition of tokens. And so on the right-hand side are regular expressions, and then some terminal from this context-free grammar. Oh, did I pass it? No. So some terminal from this context-free grammar is what we're capturing. So let's continue on. So the specification in 2.3 begins with rules for the language's reserved keywords, F, I, and P. The specification for ID uses this pipe or bar symbol to specify a union of 4 sets. So we can just think of this as an inclusive OR. Each a range of characters so that ID is any lowercase alphabetic character. I think we understand most of this. These just capture each of the characters in our program and give it some meaning. So here's what it looks like. So figure 2.4 is an AC program in a parse tree. So this is what happens when we actually take some program and how we break it down into these terminals. So here we have every character and how it gets broken down. So what happens with, we'll start with black. So what happens with F? So F, we can go kind of backwards through this. We know it's a floating point, which we know is part of this declarations. So this is a floating point declaration. So we know it's part of a declaration. This will go back to a series of declarations, which all come from this original program. So moving on to something else, so some identifier. So typically some variable name that we'll call B in this case. So that's an identifier. An identifier belongs to the declaration. So if we go back to the context-free grammar, so a declaration includes both a type, so like a float or an int, and it also includes an identifier, some ID. So there's our matching pair from declaration. The same thing happens with int. So we'll just make both of these black for consistency. Since these both belong to the same upper node. So the same thing happens with this int. It's the exact same path, except here we have two levels of declarations. So we actually split this declaration into a single and multiple back to a single. And then this multiple will just go to lambda, which means that we just ignore anything after it. So then we look at things like statements and what statements are comprised of. So we have a statement, gets broken up into an ID, an assignment, and then a value and an expression. Here, we're just doing a is equal to 5. So all we need is some value here. So just some integer number, and we specified 5 down here. So then and this of course goes back up to our statement, which is underneath this program still. And we can kind of see how the rest of this will play out. It's the same kind of path where we have statements getting broken up to in single and multiple statements. This statement, single statement, gets broken up into expressions, IDs, assignments, values, and then further expressions, values, etc. And we break down the values into floating point numbers. An expression will be, say, plus or minus some ID, so on and so forth. So fairly simple, fairly simple. We see that these trees can get pretty big, but the core idea behind them is we take some simple context-free grammar and we just do some splitting and some remapping, and we can build these parse trees. And so this is actually what a compiler does. It builds something called a parse tree. So let's look at the phases of a simple compiler, because that is, of course, what we're interested in. We want to build a compiler. So the rest of this chapter presents a simple compiler for AC. So that's this adding calculator. So we do addition and subtraction. And we want it structured according to the figure 1.4 on page 15. And that was just some simple boxed figure where we do some scanning, we do some tokenizing, going all the way till we create a machine language. So here is all those steps that we talked about. So first is a scanner. So the first thing we need to do, of course, is we need to read our program. So our program is going to be a text file, so we need to read it and produce a stream of tokens. So we need to take some arbitrary program, we need to throw out all the things like comments and white space, and we need to take that and turn it into these little tokens. So after that, we have the parser. So the parser process processes tokens produced by the scanner, determines the syntactic validity of the token stream, and creates an abstract syntax tree suitable for the compiler's subsequent activities. So given the simplicity of AC, we write its parser ad hoc using the recursive descent style presented in Chapter 5. So we don't need to know much about this yet, but we'll get into it later. So while such parsers work well in many cases, Chapter 6 presents a more popular technique for generating parsers automatically. Okay, so the abstract syntax tree by the parsing task is next traversed to create a symbol table. So what do we do in the symbol table? We associate type and other contextual information with a variable used in our AC program. So if we have something like an integer or a float, we want to make sure that we don't lose that somewhere. So we want to associate it with its type, some variable. So most programming languages allow the use of an unbounded number of variable names. Techniques for processing symbols are discussed more generally in Chapter 8. So as we already saw with our program, we're only going to be handling, I think it was 23 different variable names. Rick161, thanks for doing what you do, man. Not a problem. I have fun teaching. Okay. Here we have the abstract syntax tree is next traversed to perform semantic analysis. So we already did syntactic analysis, so now we need to do semantic analysis. So for AC, such analysis is fairly minimal because we have a very small language that only does additions and subtractions and maybe will print something. So for most programming languages, multiple passes over the abstract syntax tree may be required to enforce programming language rules that are difficult to check in the parsing task. So once things get very complicated, we can't just guarantee that we'll do it right on the first try. Sometimes we need to do multiple passes. Semantic analysis often decorates or transforms portions of the abstract syntax tree as the actual meaning of such portions become more clear. So we can make the direct analogy to reading a book. As we read a book more and more, it becomes more clear, and what we have as an understanding of that knowledge becomes better. So the same thing happens with an abstract syntax tree and multiple passes and during our semantic analysis. So for example, an AST node for the plus operator may be replaced by the actual meaning of plus or addition, which may mean floating point or integer addition. So finally what happens? So this abstract syntax tree we created is traversed to generate a translation of the original program. So here we need to know a little bit about what we're assigning to. So things like what registers do we have access to? So for register allocation. And then we also add some optimizing stages in here. So we're not just going to do some direct one-to-one translation. Oftentimes we want to make our program a little bit better than maybe the programmer even intended. So this is actually, there's a fun thing that we can kind of stop and think about here, and it's how GPU programming works. So something like CUDA. It's actually a very interesting thing. So with most CPU type programs, compilers are very, very good. And it can take a decently or an okay written program, and it will give you something that runs reasonably well. Of course, if you really know what you're doing, you can squeeze every last bit of performance out. But for the most part, you know, the compiler and then the hardware itself can give you a lot of speed up. However, if we're talking about GPUs really have a hard time, at least the compilers for GPUs. So something like NVIDIA's compiler for CUDA, NVCC, it actually has a decently hard time optimizing a program that is written in just like C or C++ because there's so many threads to manage and there's so many resources to manage that it's very, very hard to create something that would be, say, optimal. It has too many things to kind of keep track of. So a lot of times, as compared with CPU programs, you get a lot more garbage in, garbage out. So if you write bad code, you're going to get really bad results. And that's really just exacerbated on GPUs. Okay, so we talked about tokenizing. So we need to get more into scanning and what scanners do. So what does a scanner do? Its job is to translate a stream of characters into a stream of tokens. So we need to take these characters and we need to give them some meaning in terms of tokens. So rigorous methods for automatically constructing scanners based on regular expressions. So we use those regular expressions to map characters to tokens are covered in chapter 3. So we'll see that next chapter. So here the job at hand is sufficiently simple to undertake manually. So figure 2.5 shows pseudocode for a basic ad hoc scanner that finds tokens for the AC language. So let's look where 2.5 is. So a fairly simple code that we can run through very quickly. So what happens here? So we have some function that we just call scanner. So we're going to run this scanner on some code that we have, some input text file, and we're going to return a stream of tokens. So while it's not empty, while we don't have an end of file, we're just going to keep going. Otherwise, our last token is this dollar symbol, which we know is the terminator of the entire program. So if the first thing we see is a number, so this s.peak, we can just think of this as some kind of read. And so if it belongs to, so this is a symbol for belonging to, if it belongs to this set of numbers, so 0 through 9, we know that we're going to scan digits. So we want to take in some digits. If it's not a number, then we know it's a character. And so then we need to check what kind of character it is. So we need to see if it's some character but not an identifier. So this is for integer, float, and print. So we need to check that if it's some legal ID. If it's not some legal ID, well, is it a float? Is it an int? Is it a print statement? If it's none of those things, we then need to check, okay, well, is it an assignment? Is it an addition? Is it a subtraction? And then if we found out, oh, these aren't any digits, or oh, this isn't a float or an int or a print statement or some assignment or arithmetic operation, then we'll just automatically go to this default statement, which just calls a function that says, hey, something's not right. You put something in this program I can't understand. So if you write that meme B letter in your C program and you try to use it as a B, you're going to try to compile it, and then GCC is going to yell at you. It's going to say, I don't know what this is. What are you trying to do to me? Okay. So that's the basic idea of how a simple scanner works. Let's see. Did we skip over anything interesting? We can cover a couple things. So a token's type explains the token's membership in the terminal alphabet. All instances of a given terminal have the same token type. A token's semantic value provides additional information about the token. So here we're talking about two different types of value, so semantic value, and then also this membership. Let's see. So this is just explaining the program, so we can skip most of that. So let's talk about parsing now. So the parser is responsible for determining if the stream of tokens provided by the scanner conforms to the language's grammar specifications. So the grammar serves not only to define the syntax of programming language, but also to guide the automatic construction of a parser. So here we're just kind of saying that if we do a good job at specifying a grammar for a language, then we can oftentimes use tools that will automatically give us things like scanners and parsers. And we skipped over this a little bit. I didn't even see this. So this is just the scan digits function. And so all this does is it checks to see if there's a space. If there's no space, it checks to see if it's still a number, and it just constantly advances. Then it checks to see, oh, did I hit some decimal point? If I didn't hit a decimal point, then I know it's an integer. If I did, I know that it's a floating point. And then we continue on, and we want to read, if it's a floating point, we want to read the remaining digits after the decimal point. So there's that. So let's talk about recursive descent. So recursive descent is one of the simplest parsing techniques used in practical compilers. So the name is taken from the mutually recursive parsing routines that, in effect, descend through the derivation tree. In recursive descent parsing, each non-terminal in the grammar has an associated parsing procedure that is responsible for determining if the token stream contains a sequence of tokens derivable from the non-terminal. For example, the non-terminal statement is associated with the parsing procedure in 2.7. So where's 2.7? So here we have 2.7, and remember from the context-free grammar that we saw that statement could be split up into multiple different things. So let's go back to that context-free grammar. It'll be useful for us to remember that. So let's look specifically at statement. So we know that statement itself can be split into either some identifier, an assignment, a value, an expression, or it can be split into just some print ID. So this will be the code that kind of realizes these kinds of rules. So let's get back down to it. So we have some procedure. We first check to see if it's an ID. If it's not, or if it is, we match that it is an ID. So we call this match. Then we call the match that we know that it must be an assignment. And then we call two other things, these value and expression. Values and expressions are non-terminals, so they have to have their own statements. So then we have to see, okay, well, if it's not an ID, we know that the only other thing it could be is a print. So we have to check if it's a print. If it is a print, we have to match the print statement and then the following ID statement. However, if it's not a print, we know, okay, well, I didn't see an ID and I didn't see a print. This isn't what statement should break into, so I call an error. Okay, and this is just going over what we just went over. So we can skip that. So here we have something for statements. So we knew from this context-free grammar that statements can be broken up into two things. It can either be a single statement followed by more statements, so it would recursively call itself, or it can just go to nothing, some lambda. So lambda we can always think of as nothing. Okay. So we'll run through this real quick. So in statements, we check if it's an ID or if it's a print. If the next thing is an ID or a print, we know that we need a single statement because a single statement will break into IDs and prints, or IDs and potentially prints. And we also know that we're going to need another statement here, so we're going to recall ourselves again. Now, we also know that, okay, we can also just go to nothing. We can be this lambda. So we know that if this is the top level statement, so if we go back to this big example where we decoded some entire program, we know that if it's an original statement, we know that if this statement is lambda, we have to immediately follow it by some terminating character, being this $sign. So then we check in the program if we see this $sign. Because if I'm statements and I'm the original one, I want to check if I'm done. So if we are done, well then of course I should do nothing. So do nothing. However, if I do something and I see a terminating symbol, that's a problem. I'm not supposed to do that. So we call an error. So implementing the production. So once given production has been predicted, the recursive descent procedure then executes code to trace across that production, one symbol at a time. For example, the production statement breaks down into ID, some assignment of some value and expression. In figure 2.7, derives 4 symbols, and those will be considered in the order ID, assignment, value, expression. The code for producing these symbols, shown at markers 2, 3, 4, and 5, so if we go back to 2.7, so 2, 3, 4, and 5 are produced by calling these functions, so calling some match to ID and assignment, and then calling separate statements for value and expression, because we remember value and expressions are non-terminating symbols. Okay. So here's what an abstract syntax tree for that simple program that does something like 2 adds looks like, or will look like from the view of the compiler. So from some program, it gets broken down into having some assignments of a float, some assignment of an int, and then using these things, we have some assignment statements. So we're going to take this initialized value of a, we're going to add some number, so some integer number 5. Then we're also going to assign some integer number b, the result of doing some addition, so this assignment will break into some addition plus an expression. And the expression is going to have some identifier a and some value, in this case, some floating point number. And then finally, the final statement that program breaks down into is just a print. So if we look back to this original tree that we had, this parse tree, we see it's very similar. We've really just cut out some of the middle pieces. So if we erase a lot of this highlighting, well, what have we kept in that abstract syntax tree? Well, let's get out a pencil and let's make it red and a little. We kept this program bubble, but then we don't really care about a lot of these intermediate stages. So we can really just say, okay, well, we'll have some float, and we're going to have some integer of f and I. And then the next thing we're going to do is we're going to have some statement. And we're going to have, but we don't even need the statement. We could just say, okay, well, we're going to assign something. And we're going to have this some ID and some integer number. And the same thing goes down the line. We're going to have more statements, but we really just care about things like IDs, assignments, more IDs. We really just want to kind of cut out all these middle pieces here, as many as we can. Because we've already done the heavy lifting to figure out if it's correct or not. So we really just want to make it simple. So we just care about some declarations, some assignments, and then if this assignment is an ID and then some operation, we care about that as well. Okay. So this leads us to talking a little bit more about abstract syntax trees. So we've talked about context-free grammars. We've talked about regular expressions. We've talked about how we can build these kinds of trees that can represent our language and how we can use context-free grammars to build these trees. But we still need to talk about what an AST or an abstract syntax tree is. So the scanner and parser accomplish the syntax analysis, determining if we have something that's valid or syntactically valid. To ensure that the compiler's input conforms to a language token and CFG specifications. So while the process of compilation begins with scanning and parsing, following are some of the aspects of compilation that can be difficult or even impossible to perform during syntax analysis. So this basically saying that, listen, I don't know if you guys just heard that train horn, but that was mighty loud. Okay. So most programming language specifications include prose that describes aspects of the language that cannot be specified by a context-free grammar. So for example, strongly typed languages insist that symbols be used in ways consistent with their type declaration. For languages that allow two types to be declared, or new types rather, a CFG cannot presuppose the names of such types. So this is just saying that if we have a language where we can do a type def, so we define our own type, we can't specify a context-free grammar that encompasses all types. So we're going to need some other kind of checking. So some languages, and so this goes back to this context sensitivity. So the operation that we're doing on some variables depends on the context of, say, what these variables are. So if we look at something like Python, for an example, so with Python, if we do addition, if we do, 1 plus 7, we're going to get the number 8 out. However, if we do something like the string AB with the string CD, it concatenates them into ABCD. So there's some context that determines, say, what addition does in that circumstance. Some languages use the same syntax to describe phrases whose meaning cannot be made clear by a context-free grammar. For example, the phrase x.y.z in Java could mean package X, class Y, static field Z. But the same phrase could also mean local variable X, a field Y, and another field Z. So we may have multiple different ways of, or one way of, say, accessing something, may work for multiple different, say, tiers. And so most languages allow operators to be overloaded to mean more than one actual operation. For example, the plus might mean numerical addition or the appending of strings. So this is that Python example I just gave, actually. For relatively simple languages, syntax-directed translation can perform almost all aspects of a program translation during syntax analysis. Compilers written in this fashion are arguably more efficient than compilers that perform a separate pass over the program for each phase. However, from a software engineering perspective, the separation of activities and concerns into phases makes the resulting compiler much easier to write and maintain. So we have to remember at the end of the day, we have a limited amount of time. If we get put on a software engineering project, we can't spend 9 years on something and produce something that's, slightly better than what could have been done 8 years ago. We need to think practically. So if a large group of people are going to be maintaining a project, we probably don't want one giant file that has all the information in it, and we don't want all the stages to be intertwined. Having some modularity is often very nice in a large project. So let's see. So it's common practice to create an artifact of syntax analysis known as an abstract syntax tree. So this structure, this abstract syntax tree that we're going over, contains the essential information from the parse tree, but inessential punctuation and delimiters. So this is going to include things like braces, semicolons, and parentheses. We're going to ignore those. So these aren't going to be included. So figure 2.9 shows us an abstract syntax tree. For the parse tree, figure 2.4. So let's see 2.9. We passed it. So here's 2.9. It's some abstract syntax tree. And as we kind of saw earlier, this is heavily reduced from that parse tree that we saw originally. We're getting rid of all these intermediate steps of breaking down program into classes of statements. We really just cared about the end result in an abstract syntax tree. So the abstract syntax tree is just a common intermediate representation of the program for all phases after syntax analysis. So such phases, so sometimes we may add some information to this abstract syntax tree. So we already have a reduced version, but sometimes it's really useful for us to add some stuff. So we decorate it with more information. And so this gives us, some more context about what's going on in the program at these different points, and we can maybe do some things like optimizations. So thus, the needs of the compiler's phases must be considered when designing the abstract syntax tree. So for the language we're using, these are the things we have to consider for our abstract syntax tree. So declarations need not be retained in source form. However, a record of identifiers and their declared types must be retained to facilitate symbol table construction. So we need to make sure that at least somewhere we're remembering, what the types of these variables are going to be, so that when we make our symbol table, we have that information. And then also for things like semantic type checking. So we said that we can convert integers to floats, but we need to make sure we're not trying to convert floats to integers in this language. So the order of the executable statements is important and must be explicitly represented so that code generation can issue instructions in the proper order. So this is an interesting one because in reality, the instructions will execute out of order in the processor. However, we're assuming some very, very simple, very simple system here where we write some sequential program, it executes sequentially. Okay. An assignment statement must retain the identifier that will hold the computed value. So we need to know where a value is being stored. And we also need to know the expression that makes that value. So each assigned node in figure 2.9 has exactly 2 children. We can see that up here. So assign is going to have to have some identifier and number. And so here this assign has an identifier, and that number is created by this expression, identifier plus this number 3.2. Okay. What else do we have? Some last considerations that we need to make for our abstract syntax tree. Nodes representing computations such as plus or minus can be represented in the AST as a node specifying the operation with 2 children. So that's what we just saw with the addition, that plus. And then finally, a print statement must retain the name of the identifier to be printed. So we have to know what we're printing, of course. So it's common to revisit and modify the AST's design as the compiler is being written in response to the needs of various phases. So object-oriented design patterns such as visitor facilitate the design and implementation of the abstract syntax tree, but we'll talk about this much later, about 5 chapters from now in chapter 7. So we've talked about syntactic analysis. We've talked about building something like an abstract syntax tree, and building a parse tree. But now let's move on to something a little more that we may need to be a little more clever about, which is semantic analysis. So it's a catch-all term for any post-parsing processing. So after we do the parsing, this really covers the meat and potatoes of the rest of what we need to do. So this is going to enforce the aspects of a language's definition that are not easily accommodated by the syntax analysis. So things that can't be fit into the CFG, the context-free grammar. So this is going to include declarations and name scopes. So if something's not a global variable, maybe we can't use it everywhere. If we define a variable in a function, well, can we use that variable outside a function? Probably not, so we need to check for that. However, if we're just parsing it, we may not recognize that. We may see some, let's write out an example. So if we have some function, and it says I have some integer a, and then this function ends, and then I have some main function, and then I try to do some print a. Well, is this going to work? Well, this statement is okay. I can declare an int in a function. There's nothing wrong with that. And then once I'm in this main program, well, there's nothing wrong with printing out a variable. However, the scope in which this variable is valid, that's something that just the syntax isn't going to tell us. So we need to be a little more clever, and we need to do semantic analysis. So language and user-defined types are examined for consistency in semantic analysis. And then also operations and storage references are processed so that type-dependent behavior can become explicit in the program representation. So we're going to focus on two things as far as semantic analysis goes for this small language we're using, and that's going to be things like symbol table construction and type checking. Remember, this is a very small, very simple language, so we want to condense the work we're doing to just build some core ideas. So let's look at symbol tables. So with a symbol table, what are we talking about? So in this adding calculator language, AC, identifiers must be declared prior to use. Makes sense? I think every language does that. Well, except for, yeah, every language does this. You have to define a variable in order to use it. Even in Python, you don't declare it as an integer or something, but you have to, say, give it a value. So a equals 5. But this requirement is not easily enforced during syntax analysis because we may, like we said earlier, we may be using something, but we're not really looking at the history of what's around us to see, is this valid, is this not? So symbol table construction is a semantic processing activity that we look over the entire abstract syntax tree. We record all identifiers and their types in a symbol table. In most languages, the set of potential identifiers is essentially infinite. And this is because if we think about, say, in C or in Python or in Java, what can we name our variables? Well, really anything. A, B, ABCD, dog, cat, anything. So, but here we only have 23 distinct identifiers because remember we're only using single characters for identifiers. And we're ignoring, what was it? It was A, S. Oh no, sorry, we're ignoring P, S, and F. No, what was it? Oh, no, never mind. It was integer, float, and print. I, F, and P. So all letters, 26 letters, minus those 3, 23. As a result, the AC symbol table has 23 entries. And we'll indicate each identifier's type as either an integer, float, or null. So if we're not using it, it'll be a null. Integers will be I, floats will be F. So in most programming languages, the type information associated with the symbol includes other attributes, and this will be things like scope, visibility, storage class, and protection properties. So this will be more important if we're building a more complex language where things like scope and visibility will be an issue. But for our simple language where we're not doing things like functions, this works just fine. We can ignore things like scope because we're just going to have a simple program. It runs down the line sequentially, does the instructions, terminates. So to create this symbol table, we traverse the abstract syntax tree counting on the presence of a symbol declaring node to trigger appropriate effects of a symbol. So if we went back to that simple example before where we declared A and B and then we did some addition, we would see the symbol table would look something like this. So A and B, A would be an integer, B would be a float, so they would have a type associated with it. We notice that we skip P, we skip I, and we skip F, because those are special symbols. So this can be arranged by having nodes such as float declaration and int declaration implement an interface or inherit from an empty class, such as SymDeclaring, which implements a method to return the declared identifier's type in figure 2.10. Visit SymDeclaringIn shows the code to be applied at nodes that declare symbols. So let's look at figure 2.10. Here we go. So basically, when we get something that says, oh, we're declaring something, well, we first check, okay, well, what's the type? All right, if it's a float declaration, then we're going to enter it as a float. Otherwise, we're going to enter it as an integer. And then we have another function. So our enter symbol will be for our symbol table. So for this other function, we get a name and a type. So the name is just in.getID. So getID presumably just takes a character. So then we look at the symbol table and we first check, okay, if the symbol table at that name, so if say A is null, well then we're going to change the type at A to this type. However, if something's already been declared there, like say if we had something at A, say this was A, and we tried to turn this to a float, and it was already, or say A was a float and we wanted to turn it to an int, well, we'd get this call error saying that we're trying to duplicate declaration of something using the same name. Hey Bone Throne, how are you doing today? I'm glad that you're with us. I'm happy you're here. Okay, and then we have another thing for looking up symbols. And so all this is going to do is it's going to enable us to go to the symbol table and it's going to return the type for whatever symbol we're implementing. So if say A was a float like we set up here, if we looked up the name of A, we'll return a type of float. Okay. So now that we've talked about symbol tables, we need to talk about type checking. Type checking being making sure that if we're not allowed to say cast from a, or if we're not allowed to cast from a float to an int, we need to check to make sure that that's not what we're doing. So we only have two things we need to check for, integer and float, and all identifiers must be declared in the program before they can be used. That's just something that we defined in our language. So after the symbol table has been constructed, the declared type of the executable statements can be checked for type consistency. So this is this idea of we're making sure that everything's of the correct type before we try to run anything. So most programming languages include a type hierarchy that compares the language's types in terms of their generality. So our AC language follows the tradition of Java, C, and C++ in most languages, at which float type is considered wider or more general than integer. So what we mean by this is that all numbers included in integer are a subset of the numbers of floats. Because if we think about every integer, integers can be 0, 1, 2, 3, ... However, a float can be 0, 1, 2, 3, but also 3.3, 4, 5, anything. So we'll just consider this a subset. Oops. Okay. So on the other hand, narrowing a float to an integer loses some precision for some float values. So if we converted something like a float to an integer, if we converted 3.45 to an integer, it would have to be either 3 or 4. It couldn't be someplace in the middle because that's not what ints are. That's not what an integer is. What are we even trying to do there? So most languages allow automatic widening of type, so an integer can be converted to a float. But on the other hand, a float cannot become an integer in most languages unless we explicitly call for the conversion. And so this is this idea of casting. So once symbol type information has been gathered, AC's executable statements can be examined for type consistency of type usage. So this is called type checking. So after we've created this symbol table that has a collection of all the types, we can look at all these assignment statements and we can see, does this actually fit? Or are we trying to give the number 3.45 to A, which might be an int? So this is going to be that type analysis for AC. So here we're going to be visiting, we have some procedure called visit. We give it some computing statement. We pass it to something else called consistent. So let's look at consistent first. So what does consistent get? It gets two different things. And so this is going to be for, it looks like for typecasting. Let's see. Okay. It's probably easier if we just try to read what they say it does and then look back at it. So the consistent method is responsible for reconciling the type of the pair of AST nodes using the following steps. So the highest level function is going to be this consistent method. So what does generalize do? It determines the least general or simplest type that encompasses its supplied pair of types. So if we say had an int and an int, it would be an int. If we had an int and a float, well, it would have to be a float, because we have to go from an int is just a more specific version of a float. It's a float minus all the fractional portions. So this is what we mean by the most general or the least general type. Or actually, it would be int, right? No, if we want the least general type, it would be int, because a float is more general than an int. Okay. And then convert text whether conversion is necessary or possible. And let's see, if conversion is attempted from integer to float, then the AST is transformed to represent this type conversion explicitly. Subsequent compiler passes can then assume a type consistent abstract syntax tree. So let's see if we can understand this code now. So up here we have this visit, which basically just means we're going to be looking at all these things and checking types. So then we can look at the type checking utilities. So for consistent, we're going to be calling generalize. Generalize, we're going to be figuring out what the types are. So we're going to check if either of them are float. If either of them are float, then we're going to return float, because that's the most general type that we have in this small language. Otherwise, we're going to return integer. Then we're going to say, okay, well, can we convert something? So if the type of n is a float and t is an integer, so if we're going from a float to an integer, we can't do that. It's an illegal type conversion. However, if we're doing something like an integer to a float, then we simply, we're going to have some code in here that replaces the symbol table lookup for, say, n with some new symbol for now representing, so this is going from float to int, so it would be some int would be now a float in the symbol table. So after semantic analysis, we would just have to do some type of conversion here. So we would decorate this abstract syntax tree. And instead of just having, say, IDA and some float number in here, we need to make sure we're operating on the same types of data. And so we have to add another node that says int to float node. Okay. So now that we've talked about generating an abstract syntax tree and generating a symbol table and doing the syntactic and the semantic analysis, so now we need to really look at code generation. So the final task, what happens after we have this abstract syntax tree? How do we actually get to the assembly that we're so dying for? So the final task undertaken by a compiler is the formulation of target machine instructions that faithfully represent the semantics, i.e. meaning, of the source program. So this is called code generation. So exactly what it sounds like. So in a stack machine, which is that type DC language that we want to convert to, most instructions receive their input from the contents at or near the top of an operand stack. The results of most instructions is pushed on the stack. So something like C# or Java are frequently translated into a portable stack machine representation. So we're going to talk about this more in chapters 11 and 13, but we'll at least get some general sense of how this is done for our very simple language. So the AST, we already saw, was transformed and decorated with type information. We saw that back up here, we had to add some type information, especially here, where we were trying to add an integer and a float. We had to make sure that we included some extra decoration on here, that we needed some type conversion. So code generation proceeds by traversing the abstract syntax tree, this decorated abstract syntax tree, starting at its root and working towards the leaves. So as usual, we allow a visitor to apply methods based on the node's type, as shown in figure 2.14. So this is 2.14. Okay. So let's go through each of these methods in here before we break it down. So visit computing in generates code for a plus and minus. So if it's some computing step, this is the function we call. So first, the code generator is called recursively to generate code for the left and right subtrees, and resulting values will be at the top of the stack, so the appropriate operator is then emitted. So look at computing for a second. So for computing in, we call cogen for inChild1, we call cogen for inChild2, inChild1 and inChild2 being the two leaves that we just touched. And then finally, sum operation. So add or subtract in our case. So for something like assigning, causes the expression to be evaluated. So code is then omitted to store the value in the appropriate DC register. The calculator's precision is then reset to integer by setting the fractional precision to 0. So we have a marker to determine whether or not it's floats or ints. So in this target machine, we don't have the ability to just say, oh, it's a float, oh, it's an int. So we have some marker, some 0 marker. So then we have this visit sim referencing, which causes the value to be retrieved from the appropriate DC register and pushed onto the stack. Then we have printing, which is tricky because DC doesn't discard the value on top of the stack after it's printed. So the instruction sequence is generated, or SI is generated at marker 16, thereby popping the stack. Let's look at 16. So after we do some print, we want to pop that value off the stack because we've already used it, we've already printed it, we don't want it anymore. And then we have some converting nodes that we're able to change from integer to float at marker 17. This is accomplished by setting DC's precision to 5 fractional decimal bits. Remember, we define our floating points to be some arbitrarily sized integers that have a fractional portion of at most 5 decimal places. So figure 2.15 shows how code generated for the abstract syntax tree, and figure 2.9, each section shows the code generated for a particular subtree. So here we have our first thing, say a equals 5. So the first thing we do is we push 5 on the stack. We pop the stack, storing S, the popped value, in register A. So we pop the value of 5 into register A, and then we reset it to integer here. Then, next, we load register A. So we want to load that onto the stack. Then we set the precision to float. So we set this precision register K to 5 decimal bits, or decimal places. We push 3.2 onto the stack, so we can do this by just writing in the number in this machine code. We then do an addition. The addition implicitly pops 2 operands off the stack, and their sum is pushed onto the stack. Then we pop the stack with the result, storing it in B, so store in B whatever's on top of the stack, and then of course we want to set it back to integer, so 0 bits of precision in K. Then finally, we want to push the value of the B register onto the stack, so we load B. We then print the top of the stack with just P, but then we want to clean off the stack. So then finally, we pop the stack, storing into the I register. So into some register I, we just pop the value off just so the stack is empty. So even in this ad hoc code generator, one can see a principled approach. The code sequences triggered by various AST nodes dovetail to carry out the instructions of the input program. So although the task of code generation for real programming languages is far more complex, and it actually includes many optimizations, the principal ideas still hold. So if you've been around for the computer architecture lectures, the operating system lectures, or the computer networks lectures, or the logic design lectures, you see that many times we're just going back to these fundamental key principles time and time again. Okay, So this finishes our tour of the AC language. So we've effectively built a language today. We've built a language based upon some very simple concepts. So let's do a kind of review. Looks like we actually didn't take much time to go through this chapter of the book today. So that's good. You guys can all go home early. I won't assign any homework today, I promise. So let's see what we did. So first, we looked at context-free grammars and how that we can represent some arbitrary program using these context-free grammars by this idea of expanding them out over and over and over to represent the entire program. We then saw how we can use regular expressions to map just characters to these specific spots or these specific symbols in this context-free grammar. And we're using our adding calculator language for this. So very simple language. We then saw how we can build a parse tree out of this idea of expansion. We then saw that we can write some very simple code in something like C or really anything we wanted. If we wanted to manually design something like a scanner and a parser, we saw that really it's a lot of case statements. Then we saw, okay, now that we've done some syntax analysis, what else do we have to do? So it turns out that syntax analysis doesn't fix all of our problems for us. It turns out that there are some problems that won't be caught just by syntax, and only gets caught in semantic analysis. So things like type errors. Syntax won't say whether adding two numbers is the type error, so we need some semantic analysis to determine that. Or things like scope. So we need to determine if something's in the correct scope or not, or whether or not it's valid. And so we saw that we can build up things like symbol tables that will keep track of all of these things like scope and things like the type for us. And then we also saw how that we can do type checking using the symbol table in order to fix a lot of these problems. And then we saw that for code generation, we can write some fairly simple code based upon what we know about our language and what we know about our decorated abstract syntax tree, and also what we know about the instruction set architecture for the target language. And we saw how we can, say for a stack-based architecture, how we'd be able to generate code for a simple expression such as set a equal to 5, set b equal to a plus 3.2, and then print out the result of that value b. And we saw how that would look in this machine-generated code. And so there we have it. We have a fully functional compiler. Pretty simple, right? So what are the key takeaways? The key takeaways are this is a process, compilation, that we can break up into some very distinct steps. So we see that it's important to have this modularity so that if the language changes or the instruction set changes, we don't need to change the entire compiler. We may only need to change the front end or the back end. What did we also learn today? We learned that we can represent very, very complex programs. Here we're looking at something fairly simple, but we also saw that we can look at things that are fairly complex, and we can break them down to these very small, very simple components. So things like that context-free grammar table, or that those rules for context-free grammar. We saw that an entire language can be broken down into 3 symbols. It could be broken down into, or even one symbol, program, which can be split into multiple symbols. Yeah, so that was fun. We went over a basic compiler today. So what will we be going over next time? Exercises. So now that we've seen an example of a simple compiler, this brings us to the point where we need to reevaluate what we've learned so far. So we've learned it for a simple language, and we've learned it practically for a simple language. If we were to design a scanner for an arbitrary language, how would we go about that? And so that's going to be the focus of this next chapter that we'll get into next Tuesday at 7 p.m. EST, which will be scanning, theory, and practice. I had a lot of fun today. I think we learned quite a bit. I know I learned quite a bit. The more I get to learn about compilers, I think it's better for me. So one thing that you guys should keep on the lookout for is that pretty soon I'm going to be uploading some YouTube videos. They're going to be much shorter than the ones that we have today. So the ones that I've been uploading recently are just the VODs. The VODs being anywhere from 1.5 hours to when it's a short day like today, to as many as 4 hours if it's a computer architecture day. It seems like computer architecture books like to keep everything in a single chapter, while books like compilers have 20 chapters in the same sized book. I don't know any reasoning behind this, but hey, it seems to just work out that way. So, if you guys are interested, please send me a message. If there's anything you want content on, I'd be happy to provide it. Reminder, follow me if you're not already. If you want any specialized content, feel free to just send me a message. I've got my Twitter below. I'm happy to respond to you. We're having a great time here. I'll stay on just a little bit longer. If anyone has any questions, any topics that they would like covered, any other areas of engineering, any advice that they might want. I'm also looking at starting a podcast. It's going to be called The Exit Interview. It's going to be all about, hey, what kind of jobs have you had? What's some experiences you've had at those jobs? Why did you leave the job? And then also things like school. So, went to grad school, you went to undergrad, what happened there? What kind of things did you get up to? What happened when you left? Some memorable experiences there. I think it could be fun. I'm also getting in contact with a couple corporate contacts I have in the tech field. So some people at AMD, some people at NVIDIA, some people at Dell, people that I've known, that I knew a while ago. And hopefully I can get in contact with them. They might be able to, give some interesting thoughts, some interesting ideas into these things. Any general tips for writing resumes geared towards entry-level engineering positions? Great question. So, what are the three... Let me see if I can break this down into the hallmarks of what makes a good application. So one, I would say that if you want to make a good application, you want to keep it as simple as possible. So as few words as you can put down on that paper. Nobody is reading your application fully. So get to the point, put all of the key things that you really want to shine on there in bold. So a lot of times, what people will do, at least in academia, if they have published papers, they will only include the papers that are most cited. B, they will have their names bolded in the citation of that paper on their resume. Secondly, you should make a resume specific for every job you apply to. Not just you make a good resume, make a specific resume for every job you apply to. So if I'm applying, when I was applying to a lot of positions, or when I was in undergrad for internships, or even afterwards, I didn't decide immediately that I was going to go to grad school. That was something that I decided, during my senior year. So I was still applying to corporate positions. But you have to think to yourself. So one of the places I applied to was a research institution. The other place I applied to was, regular company that did computer engineering work. So the research institution, it was going to be something control systems related. Now, I could put on my resume, I could include a bunch of stuff that I've done related to FPGAs and a bunch of stuff related to, what's a good example? Computer architecture that I had studied. But for someone dealing with control systems, they don't care about that. It wouldn't matter if I had a degree in, chemical engineering. Or maybe chemical engineering is a bad idea. It wouldn't matter if I had a degree in organic chemistry. The job is not in organic chemistry. The job's in control systems. So you should really try to target your application for every single job you apply to. So there should be some changes. So what's my third piece of advice? Keep it to a page, of course. That's not real. That won't be my third piece of advice, but if it's longer than a page, just realize that nobody's reading your application, especially not that second page. What they're going to do is they're going to look at the front page, they're going to flip it real quick, forget everything they saw on the front page, read the second page, forget everything they read on that page when they flip back to the front page. It makes you forgettable. What's a good thing? Everything should be in reverse chronological order, of course. You shouldn't ever start with your oldest thing first. Let's see any other things. Quantifiable results. This is such a big thing. If you can say on a resume you improved some process by 30%, that's something that someone can get their head around. They can't get their head around, I made contributions to a project. But if you say, I improved this task by 75%, people like to see numbers like that. They want to pick out numbers. What else is there? That's really it for resumes. Resumes should be simple. If your resume is super complicated, you're overthinking it. Would leadership of a successful project be a valuable thing to add? Yes, of course. So if you're planning on including a project anyway, you should of course put that you were a leader on said project. So that goes with the quantifiable results. So the biggest thing is you don't want to write a book though. So the descriptions of everything you do, you should be able to get it down to like one line. It should be able to summarizable in a single line. Like if someone asks me, what do? I would be able to say, I'm a researcher in GPU microarchitecture, and I work on secure and fault-tolerant microarchitectures. That's it. That's all somebody needs to know. Because, if you get past that stage, if you get, that's when you'll have the technical interview. That's when people will actually start to ask you the questions like, well, what did you specifically do? What do you know? The resume and that initial interview, so you hand them your resume and you go, hi guys, here's my resume. And you try to get that initial position. It's all about that impression. It's not really about your technical skills at that point. Now, if you have good technical skills, great, it's perfect. But if you don't have good technical skills, or you at least need to make a good impression. But like I said, so it should really be catered to wherever you're applying. So if you're applying to some place that really wants programmers, or you're applying to a programming position, what's going to be on top of your list? Well, it should be, what languages do you know? What projects you've done in those languages? What types of software engineering methodologies have you done, like Scrum or Agile frameworks for like software development? If you're doing something that's more architecture related, something like Scrum is, someone will see that and they'll go, yeah, that's cool. But it's less relevant outside of software. So for something like a hardware position, they would go, okay, well, what platforms have you worked on? Have you worked on Altera platforms, Xilinx platforms? What tools do you know? Do you know Vivado? Do you know whatever Altera's design suite is? I always forget what Altera's is. Oh, here's a good one. If you want a job, listen, tell your friends. Get them in here right now. Tell them if they want a job, get them in here right now. I'm going to tell them the secret. This is the secret sauce of how to get a job. If you want a job, just talk to somebody. You just need to get a personal connection with someone. So a lot of times people will go, okay, I'll just send my resume out to where 1 billion people have sent their resumes and where recruiters are sending resumes. Might be tough to get a call back. Now, you got to play the long con. I hate calling it the long con. You got to play the long game on this. So you find someone on LinkedIn and then you message them and you say, hi. Or maybe you try to find somebody that's affiliated with your university and you go, hi, I'm Nick from Engineering Today. I saw that you're this position at this company. I'm currently at your alma mater, and what you're doing right now is something that I would like to do in the future. And so I wanted to see if there was any advice you could give me, or if you'd be available to talk sometime. So then gradually you start building up a rapport with somebody in industry. Is this something that's okay to do? That's the entire point of LinkedIn. The entire point of LinkedIn is to literally connect with people for this type of work. If you're not doing this on LinkedIn and you're searching for a job, you're not searching for a job. You're ignoring the fact that you have one of the greatest resources that's ever been at your fingertips. So that's the secret. That's the Engineering Today secret on how to get a job. Tell your friends. My fiance was telling me to tell your viewers to let them know that she made amazing mashed potatoes today, and that I should be jealous of the amazing mashed potatoes that she made. And guess what? I am jealous. I want those mashed potatoes. I'm hungry, man. I've had like 1,100 calories today, and it's all been protein. You know that egg diet, that green text egg diet? It's like 36 hard-boiled egg whites and 2 multivitamins a day, and it's like 1,100 calories, but like a ridiculous amount of protein. That's what that yeah, that's what I feel like I've done today. Except it was just like a protein shake, 2 bagels with peanut butter, and then like 3 fried eggs. Yeah, that's been about my diet today. Like I thought, what was the fast? I needed to before the stream. I had to go home and cook something real quick, and I had about 10 minutes because I had about like 10 minutes to cook uh, because I had to. That was the only. I got back at like 6:40 p.m. If I took the next bus, I would have gotten here like 15 minutes later than I wanted to start at 7 p.m. So I got home and I thought, what's the fastest thing I could do? So I turned on the oven. I threw a bagel in the oven. I don't have a toaster. That's one of the things that I've neglected to buy for some reason. So I threw it in the oven. I turned on a pan. I put it on like medium high. I threw some butter in. I was so impatient trying to get the thing to heat up so quickly. I After it was hot enough, I cracked a couple eggs in there. I took the bagel out while the eggs were cooking. I put peanut butter on the bagel, and then I went back to the eggs and started butter basting them a little bit because I was making fried eggs, so I wanted to cook the top a little bit so I didn't have the little film on it. And then yeah, I cooked that in like between like 5 to 8 minutes, and then I had about 5 minutes to eat, and then I had to walk out the door again and catch the next bus. It was a busy day. But it's okay. Someone subscribed using Twitch Prime yesterday, and I appreciate them. It was some guy, ADB7, I think. What was it? It was... Wait, it's not showing up on here. Yeah, ADB7. ADB7 was my first Twitch Prime sub. If you see him around, tell him thank you. What other helpful tips and tricks can I give on this edition of Page by Page? He sounds like a cool dude. He does sound like a cool dude. Listen, anyone that supports my teaching endeavors is a cool dude in my book. Let's see. Do I have any other sound advice other than just talking to people to get a job? Here's a great idea. If you want to get a 4.0 in undergrad, here's the easiest trick that I can give you. Treat every single day, just work it like a 9 to 5 job. If you work like 8 hours a day on just school, you will run out of work. I guarantee it. And I'm not talking about do what most people do in a 9 to 5 job, which is get in, get a cup of coffee, talk with some people, sit down, log in, check some emails, do a little bit of work, go to the washroom, come back, do a little bit more work. Oh, time for lunch already. Go to lunch, take an hour lunch, come back, log in, do a little bit more work, go to the washroom again maybe, come back, talk with a couple people on the way back, then go off to, do a little bit more work, and then kill the last hour of the day from 4 to 5 p.m. talking with people. So if you treat it like an actual 9 to 5 job, though, like if you work from 9 to 5, just on schoolwork, I guarantee it, you can get a 4.0. The thing is, most people don't do that. Most people they'll say, oh man, I stayed up until 3 a.m. studying last night. It's like, why? Just learn it ahead of time. I've yet to come across a class where I would need to stay up until 3 a.m. to study for. If you just learn it ahead of time, you never have to do that. I guarantee it. There's always alternatives to that. Not to mention, you're not going to get any better at a class in that window from like 9 p.m. to 3 a.m. You're not. You're probably only going to get as good of a grade as the couple of hours you spent leading up to that time, because all of your knowledge is going to be based upon memorization, not going to be on some foundational understanding of material. That's my hot take on that. Yeah. You see the cool picture I posted? This is a picture of the lab, guys. Let me look it up again. Where is it? Where's my... Here we go. Here's the face reveal that everyone's been waiting for. There you go. That is what engineering today looks like. That is the true face of engineering today. The sweet leather jacket with the French cuff dress shirt and the tie. Nice hair. Listen, I got that wavy stuff going on, man. I got the wavy stuff. I've got shorter hair now. It's a little bit shorter. It was longer back then. I need to get a haircut though. But this is the lab. You see right behind you where that window is? I'm looking at that window right now. This is the lab. Okay. So, I think I'm going to cut it here for today. I think we learned a lot about compilers, and I think I can spend the rest of this time trying to make some of that short form content that we've been talking about. That way I can get, maybe even like 5 to 6 videos uploaded tonight or tomorrow morning. That would be ideal. But in any event, I want to thank you all for joining me. It's been lovely having you here. I'm Nick from Engineering Today, and I hope you go out there and you learn something new. Adios.